Hi guys, in this video I'm going to show you how to make a classification tree using the C5.0 algorithm from the package C50. So first you're going to need to install this package if you have not already. So let's do install packages, and that's how you would install the package. Select the mirror that's close to you, and then once you have the package like I already do, it'll go through some installation, so that'll take a second, and then load the package like this. Okay. By the way, when I clear the screen, I'm doing that with Control L. Okay, so we're going to apply a classification tree, which is basically a technique for predicting a categorical feature or variable. So I want to use a data set that we all have access to again. So I'm going to use the iris data set, which is preloaded on most installations of R. You'll see that the data set has something to do with flowers, and particularly we have, seems like, let's look at the structure. We have 5 features or variables. Okay. 4 of them are numeric and 1 is a factor. In other words, this one is a categorical or nominal feature, so it takes on 3 levels. The third level, we're not seeing it here due to just the preview not showing it. Let's take a look at what that is. Okay, so these are the 3 levels of our categorical feature. We would like to be able to predict which species a flower is based on some combination or of its attributes of these features. Okay, so that seems like a pretty logical thing to do. You can go about this in a few ways. Logistic regression might be one. K nearest neighbors might be another technique you would think of using. But here we're going to use classification trees. Okay, especially because there's 3 levels. Logistic regression would have to be slightly modified and to a slightly more complex technique. Either way, this is another alternative. Okay, so we will first pre-process the data a little bit. Okay, so if you're starting with any data set, first thing that you should do is just to try to understand the data. First, you see that this data looks like it's somewhat organized, and we don't want any kind of order. So we want to basically shuffle up the 150 examples in this data. How do I know there's 150? I got that from the structure. There's 150 rows, 5 variables, 5 features. Okay, so I want to shuffle them up like a deck of cards. Okay, so the way we could do that, first off, if you want to get the same results as me, let's set our seed at the same spot. So I'm going to set my seed at 9850 because I'm about to generate some random numbers, and this will guarantee that we both get the same random numbers. Okay, so I'm going to generate 150 random numbers between 0 and 1. That's what I just did there. Okay, I'm going to call that G. And now I'm going to create a new data set which is called iris, but with a little r at the end, just reminding me that this is the randomized version. And it's going to be basically the same thing as iris, except the order of the rows is going to change based on the order of these random numbers that we just generated. Okay, so these 3 lines of code will guarantee that you get the same results as me and that your data set is somewhat shuffled, like shuffling a deck of cards before we begin to play. Okay, so now we can begin to play, so to speak. Alright, now let us remember that our objective was to predict, to classify the species. The species feature. So that's our target here, and these are all potential predictors. Okay, so to do that using C5.0, we've already loaded the package, so let's begin giving the algorithm what it needs. So that's a capital C 5.0. The first argument is the training data. So here I'm going to take the first 100 rows in the shuffled data set that I created for my training data. I'm going to leave the last 50 rows or examples for my test to see how well the algorithm does at classifying. Okay, so iris R, I want the first 100 rows, and I want to also eliminate the target feature here. So here I'm going to do -5 because this is the target, was the first, second, third, fourth, fifth column in iris_r. So by doing -5, I'm saying take the target out. These are the training data potential predictors. Okay, comma. Now I need to give it the target. So I basically it makes you separate your training set into target and predictors in that order. Sorry, not in that order. In the order of first put the predictors, comma, then put the target. Okay, and that's all you need to feed it. There are tons of other options for fine-tuning things. We want to focus on the highlights and the fundamentals here. Okay, if I hit enter here, I might get a lot of output. I always want to name my model something, so I'll call this model 1. Okay, let's hit enter. Okay, looks like things went well. I could quickly look at what happened here. I get a little output. It's not terribly descriptive. Obviously, just repeats what I called here. It tells me I made a classification tree. There was 100 examples or rows or samples. Size was 100. There were 4 predictors, and the tree size is 4. I think the way that C5.0 defines the size of a tree is with the number of leaf nodes or terminal nodes. I believe that's the way it does it. Okay, there's other ways to define the size of a tree. You can define it by the size of the total number of nodes from the root to the interior and the leaves. Okay, this is not terribly informative. We can use the summary command and get a lot more under the hood of what our model learned. Okay, so we see again some repeated stuff here, a lot of output, and here we finally get to the decision tree. Okay, it's not as pretty as the ones maybe you're seeing in your textbook with all this kind of thing going on. There are ways to make these trees. Sometimes I've been successful with making these trees without too much effort using C5.0, and sometimes I think when it's just too big, the plot gives you errors. I've Googled this problem, and it seems like you need to do quite some work. There's another package which can actually help you to draw the plot if this format is somewhat confusing to you. Okay. Also, I could recommend using rpart, which is another algorithm in another package called rpart, which will also create a tree and give you options to draw that tree as well using another package called rpart.plot. Okay, I've made a tutorial video for that, so you could check that out. Alright, so here we're going to focus on C5.0 and see if we can learn what this decision tree or classification tree is telling us. Alright, so it's telling us if we were to draw this on a little like blank canvas here, it's telling us to start splitting the training data with the feature petal length. That turned out to be the most predictive feature. Okay, so if I go left and right doesn't have any significance, but let me just do, if I go left, less than or equal to what, if the petal length was less than or equal to 1.9, then the prediction, let me make my leaf nodes round, just my convention, is setosa. And by the way, out of the 100 training examples, 34 ended up in this direction, in this leaf. Okay, now we can go the other way. So the other possibility is that the petal length is greater than 1.9 inches, centimeters, probably centimeters. Okay, if the petal length is greater than 1.9, this tree continues to grow. So we don't get to a leaf, we get to another decision node. Okay, we're going to split this subsets into by petal width now. So that was another feature that we had available to us on all the flowers. So petal width. So we're going to split petal width, and these are, notice these are binary splits here. So this way or this way, right? So if petal width was greater than 1.6, let me write that here like this. Petal width was greater than 1.6, there is a prediction here. So these tell me that there's a prediction. So it's a leaf node. By the way, the prediction is Virginica if it's greater than 1.6. So let me abbreviate it like this. 29 of the total 100 training examples fell into, and if we have a petal width less than or equal to 1.6, we go in this direction where I'm over here, and the tree continues to grow. So it's not a petal yet. It is another, sorry, it's not a leaf yet. It's another interior node where we're going to split the subset of data that's gotten this far further based on petal length again. So you see that features can come up again down a tree. You can have subtrees that repeat as well. So length. Okay, so here, if we follow down this path, we're going to split the data, or I should say the model has split the data into petal length being less than or equal to 4.9 petal length. And if we go that way, the prediction, so we have a leaf, so you see here we have a prediction, is versicolor. So let me just abbreviate by writing versi. And 35 examples in the training set got here, ended up in this leaf. And finally, if petal length is greater than 4.9, we're gonna have another leaf node, a terminal node, a prediction, this time Virginica. So let me abbreviate again, just right, VIRG here. And 2 examples from the training set ended up here. Now if you were to add up these guys, 2, 35, 29, and 34, all the leaf nodes, you'll get 100, right? So let's just do a quick spot check. 34 plus 35 is almost 70, 69, plus 29, that's 98, plus 2, 100. And you see that earlier we were told that the tree size was 4, and we have 4 leaves. So I'm pretty sure that's how the C5.0 determines the size. But you see there are a lot more nodes. We have the root up here. We have leaves. I've drawn the leaves round. The square nodes in between are all features, basically places where we need to make decisions. And the arrows are all branches. Okay, and it's an upside down tree. Okay, so that's all well and good. So we can convert the output, and oftentimes if you're dealing with a lot larger data set with many features, you'll have a much larger tree, and drawing this might be edifying. It might kind of clarify things for you, but you should get comfortable to see it this way um, as as well as this way. Okay, so I'm gonna kind of get rid of this now and scroll down a little. We get a little evaluation on the training set, which is not the best way to evaluate a model, but it tells us that there were actually no errors, which is pretty good. I mean, that might also indicate that this model might have overfit. Okay, because that's not necessarily a great thing to have, to that your model perfectly predicts your training set. Okay, and here we get a little confusion matrix where we have the predicted classes and the actual classes and the predicted classes. Here we see that they're all that this diagonal are the correctly predicted class levels, and these guys, I'm guessing they leave them out when they're 0, but if there were any errors, you would see them here in the form of the number of errors at that kind of intersection. Okay, but much more interesting is to create a confusion matrix and see how well this model that we just created does on a independent data set, the testing data that we created. So to do that, we need to predict some observations. So we're going to predict, I believe we called the model M1, so we're going to predict using M1, and we're going to predict iris underscore R. We're going to go from 101 to 150. That was our training. That was our test set, sorry. Okay. We used 1 to 100 to train. Now we're going to test with 101 to 150. Okay. And we should probably give this a name. Let's call this P1. Okay. So if I type P1, we'll see that we get a bunch of predictions for species. Much more interesting is to see, to evaluate how well the model did on the test data, is to construct a confusion matrix. Okay, so we're going to use table, very simple command here, table. Let's put the actual species of the test data on the horizontal axis of the table. So we'll end up with a table like this. Let's put the actual here and the predicted here. That's a good convention. So to get the actuals, we need to get from row 101 to 150, and the species was column 5, and the predicted, we just can call the P1, which we named this vector here. These are the predicted classes. Okay, so we can even call this predicted, so to make it clear. All right, so let's see how well it did. So here we got the predictions, and here we got the actual species of these plants. Okay, so from the 50 test examples, the 50 flowers that we set aside for testing, the C5.0 classification tree algorithm predicted 16 of them to be Setosa that were actually Setosa. So that's a check. So there were 16 Setosas that the model also predicted would be Setosa. So that's good. There were 12 versicolors that were correctly predicted to be versicolor. There were 19 virginicas that were correctly predicted to be virginica. That's great. That's the diagonal. Those are the kind of correct predictions. Now you see in the off diagonal, in this upper triangle here and lower triangle here, you will see errors. So different types of errors. So here you see zeros. These are all telling us that there were no incorrect predictions at those intersections. But here we have an interesting case, so we could talk about this. So the model had some errors, and they were here. It had 3 out of the 50 test examples. It correctly predicted 47. So you can take that as a measure of the performance of the model here. But let's focus on what this 3 means. So the model, so there were 3 versicolor species out of the 50 examples that the model incorrectly predicted or classified to be virginica. Okay? So it made that particular error. So there were 3 versicolor species flowers in the data set, in the test data set, that the C5.0 algorithm incorrectly predicted to be virginicas. Okay. Besides that, there's no errors to talk of. As you can see, these are all 0. But if they weren't, we could discuss those in turn one by one. All right. So overall, I would say it did a pretty decent job, given this small data set and the small tree here that's easy to understand and interpret. Okay, so I hope this was helpful. I'm also going to try to do the same classification tree model for the same data, rather, using the rpart algorithm, and see the results from that, and maybe compare the two. Okay, that package will let us also draw a plot. I will say this one last thing here. I have had success drawing a plot of this tree with C5.0 once or twice, and it was always when the model was small. So I don't know if that has to do with it, but don't depend on drawing a tree with this with C5.0. So let's see if we get it here. And in fact we do, because it's quite small. So this looks very similar to the tree that I just drew, which is quite cool. And if you're able to drag it quite far, you'll see here are the leaves, okay, and here's the root, okay, and here are the interior nodes, and it's very similar to the tree that we just drew, which is quite cool. And at the leaves you get some nice info. So you see that this was setosa, this is versicolor, virginica, the predictions, right? And these numbers here have to do with the output from the summary here. So they're somehow connected to these guys. Okay, so that's quite cool. But I've tried to do this with a much larger kind of realistic data set, and I got some fatal errors, which I followed up and to no avail, except to install some further libraries. If you don't need to draw this, C5.0 is a great algorithm for doing classification trees. If you do need to draw it, check out the rpart tutorial for classification trees. I'll show you how to draw one, and that will always draw one. Okay, so I hope this was helpful. Till next time, have a great day.